All right, so welcome to test corrections for problem number 20 on the first 6 weeks test. We are almost done, so thanks for sticking through to the end. Remember, we're looking at these not just to get test corrections, although that's one of the main things, but we are looking at these in order to understand how do we solve these or how do we approach these AP Physics free response questions. We've looked at one that was a paragraph linked answer, that was number 19. Number 18, we looked at one where we actually had to try and find something. 20 is the last type, and this is where we have to come up with a lab procedure. We have to explain what we would do, and then we have to do something with that sort of concept connected to it. So this is a very common question. This is, in fact, one of the main questions that they could ask on the AP test related to kinematics. So we're just going to dive in. I'm going to start by reading the question. It says a student wants to find the constant velocity, so that's a detail word, constant velocity of a remote control vehicle, so something moving, that travels in a constant velocity. All right, for one, this said it twice. That needs to be highlighted for sure. Constant velocity is said twice. The student may only use a graph to solve for the velocity. All right, so what does that mean? May only use a graph? Well, I hope you realize that that means no, straight up at least, no math. So no straight up math. We would have to use a graph. We need to figure out what we do. Well, the question says write a brief lab procedure to collect data. That is the goal of this. You may use a timer, a meter stick, and that's it. Specify what must be recorded. So there are so many words here that I purposely put in to try and get you to think about the problems in a particular way. Well, first thing with a lab procedure is it has to be numbered. I gave you a point just for numbering your procedure. You could have told me to do something totally out of nowhere, but if you put numbers 1, 2, 3, 4, I gave you points. If you still haven't caught on, we've been doing this since the first assessment, you have to number your lab procedures. So we need to collect data, and so the first thing is we're looking at constant velocity, and we have to use a graph. So how can I get constant velocity using a graph? Well, I could either measure the velocity, but I don't have anything to measure that with. All I have is a meter stick and a timer. So this is my distance, or my position, and time. So I have to graph something with that, so I have to collect data related to that. So in the problem, I gave you credit if you simply had us collect any sort of position and any sort of time. So a lot of you said place a meter stick on the ground, which is great. The main thing with that, though, is you need to specify how are we going to measure that. Well, that's great. There's a meter stick, and so we have to have something about put the car at the start. Let's specify a little bit more of the meter stick. Then step 3 is we have to still collect data. We haven't collected anything yet. So to collect data, we're going to start our car along the path of the meter stick. So we start our car, but we need to say what to measure. Well, I need both time and my position. But here's the main thing I was hoping you would catch because I said a graph. You need more than 1 point of position and time. So we might have the origin, but what you needed to do was you needed to set something up where you recorded the time at different positions. All right, so imagine you have your car going. Here's a beautiful car. It's moving in the path of your meter stick. We needed to have multiple positions measured at multiple times. And it doesn't matter which one you decided to keep constant. You just had to pick which one. So let's say we kept time constant. Start the car along the path of the meter stick and record. Well, I need to say what to record. Record the position every half second. So realize what this does is I will probably, since it is a remote control vehicle, I will probably have multiple readings within the meter stick, and I'll record those positions. Sure enough, this is all I need to record data. My car is moving along the path, and I'm going to record the position every half second. That's all I needed. We could have changed it. We could have said record the time every 10 centimeters if we wanted. So we could have exchanged these two, and that would have been totally fine. The goal that we needed to do is just make sure we measure both time and position in our procedure. Now, a lot of you said, all right, now we have to graph or analyze data. I'm going to say it clearly on here so that you learn this time, is that graph is under the analysis. And realize the analysis section is a whole other section of the lab on purpose. It comes after the next part. So you can't say analyze because we haven't even gotten our data yet. You can't tell them record it and graph it. That's a whole other part of the lab report and has nothing to do with the procedure. Procedure is only about collecting data. What you do with it later is what part B asks. I asked, what would you graph? Well, I hope you realize that the only things I have to graph are my time and my position. How can I get velocity from time and position? Well, we only ever saw time on the x, position on the y. If this is a constant velocity graph, I should have a constant straight line. I'd be moving at a constant rate, or I'd have a constant slope, or you could say a constant rate of change. There's two things you needed to say. You needed to say position versus time graph. I may have given you credit if you just drew a graph. And what would you use to find the velocity? Well, you need to know that the velocity on this guy is the slope. This was the only answer you could possibly have. I gave you 2 points for if you said position versus time, and then 2 points for the slope. All right, you need to be specific, and when we talk about a graph, you have to say the y versus the x. A lot of you said I would put the times across the. You were like very vague. You need to be very specific. Position on the y versus time on the x, and ideally in a sentence this would have been good. So I would plot position versus time, and to get my velocity, I would calculate the slope of the graph, since the slope of the position versus time graph is the velocity. All right, now it's time for part C. So we went from coming up with a lab procedure, and then we said, well, what happens if this truck goes off the edge horizontally? So let's pay attention to detail. I said horizontally off the edge. So that says something about my direction, so that can be important. Off the edge of a shelf where it experiences projectile motion. Notice a reference to a concept. Draw a diagram of the truck with its trajectory. Well, let's start with what it said. I need my shelf. Let's say my truck is up here. Yeah, it's a truck. And we need to realize that I said horizontally. So the truck is sent off the edge horizontally. Now here's a tricky concept. I want you to realize that the truck doesn't get here and then immediately take off downwards. That's not what happens. My truck will have an initial speed back here, which it continues to until it experiences the acceleration due to gravity, which it begins to experience right as it comes off the edge. So realize here, I'm sent off horizontally, so I only have one velocity. And it's going to be this guy. This is my V0. And it is important to recognize that this is only in the x direction. So what's my velocity in the y direction? Well, my velocity amount of this guy going down initially is 0. And as time goes on, I'm going to experience this parabolic sort of shape. This is a lot like those motion diagrams we drew a while ago. Notice how parabolic this is. So what we need to do, according to the problem, was we needed to label Vx and Vy as well as the final velocity at the initial and final as well as in between. So the more the merrier in this case. So realize that there are some rules we have to follow in projectile motion. Projectile motion, we say a couple things. First, I'm going to talk about the x component, because this is the concept that this is referencing. In the x component, my velocity is constant. I'm going to just write equals constant. So everywhere I look, my velocity is going to be the same. So if I copy this guy from up here, this is going to be my velocity. So what I can do is I can do this thing for me at least, where I take this guy and I realize this one is going to be the same here and here and here and here. So I can just take a bunch of copies of this and move it wherever I want. All right, so that's what I'm going to do real quick, and I'm going to put them at every spot. So now I have all of my x components at every part. Notice my velocity is constant, never changes. And another thing we could say is my acceleration is 0. So I gave you some points if all of your x velocities were the same. Then we could do our y component and realize I start off with 0 y velocity. But in my y component, my y is increasing, so it's getting bigger, but it's increasing downward. Why is that? How can my y velocity be changing? Well, it's because my acceleration is negative 9.8 meters per second squared. So for my y component, I'm going to have different velocities as I go because I'm going to be increasing speed. Here I have nothing, so I'm going to just put a dot there to symbolize this guy. So beginning here, I'm going to have a y component going down, but I want to add these head to tail so we don't get confused, and these are kind of going to overlap. So my y component is going to start off small, but it's going to get bigger and bigger. Right? All these are my y components. And I gave you 2 points if your velocities were increasing, and I kind of gave you a pity point if you drew a parabolic shape, period. Some of us had this idea that my component was like this in the x direction, and then some of you drew this for the y direction, which you get the idea of the parabola, but you need to realize that the y direction is only the y direction. It can only go up and down. So what we do at this point is we have to connect our vectors. We need to get our total velocity, and here is how we do it. We go from our beginning to our end. Notice these are added head to tail. I do that on purpose. And so I'm adding in my resultant vector. This black arrow is actually what my velocity is. It's really hard for me to draw straight lines, but I do hope you get the idea. Notice how I'm making them arrows. A lot of us didn't put arrows, and therefore we weren't really drawing vectors. We also didn't label them. So this is my v throughout time. If you drew a triangle, I gave you 2 points because you had to know that vx plus vy gives us our final velocity. All right? And the triangle was here, and then if you labeled and got final velocity that was increasing over time, I was looking for, did you realize about the components, which I hinted at when I said horizontally. So you got to realize there's a horizontal and a vertical roll going on. My velocity in my y component is changing. It's getting bigger downward while my x component is constant. Now, if you're done your homework, you should be able to know how to calculate this angle as well as this side, or vice versa. You can get a component. And that could be useful for certain math problems we could do related to projectile motion, but quite frankly, I didn't want to give that to you because it's not majorly tested. This concludes problem number 20. So go ahead and finish your test corrections. If you have questions, come on in and get help, especially on the multiple choice. But other than that, you should now be done with your test corrections. You can turn it into the box, and I will grade it this weekend. All right, I will see you soon, and I hope you have a blessed day. Smiley face.